Okay, so today we're going to talk about community detection in the stochastic block model. Okay, the idea is to try to understand how well clustering and community detection methods, so types of unsupervised learning, work not just in the worst case type situation like how we saw for max cut where we got always the same approximation ratio, but how does it work on sort of typical data sets, right? It's hard to define what typical data sets mean, so we're going to come up with a model. I mean, I won't argue that this model is in any form modeling reality, but it's a model for a graph that does have some community structure, right? It's a random graph, and we're going to try to understand what are the computational and statistical limits of this model. Like, how well can we cluster in this model? And we're going to use actually algorithms very similar to the ones in max-cut and spectral clustering and so on, but we're going to try to understand them not from the worst case perspective, like how we did with Shiger's inequality for spectral clustering, or the approximation ratio, the Women's equivalence and approximation ratio for the SDP. Instead, we're going to try to understand how well do they work on average Anderson random data model. Okay? So we're going to start with community detection in the stochastic block model. Okay. Community detection. Stochastic block model, right? So known as SVM. Okay, and we can define it over many, in great generality, in many settings. Here I'm going to do it for just two communities, and then it's sort of clear what is meant in general. Okay, so we'll have two communities. Right, and so we want to generate a graph that has sort of a community structure for two communities. So the way we're going to do this is we draw a random graph. So a random graph on n nodes. Okay, so we're going to split the n nodes at random in n over 2 nodes on one side and n over 2 nodes on the other. And now every pair gets an edge with some probability. Right, so edges are drawn independently. Edges are drawn independently, and the probability for the edges is p if they're in the same community and q otherwise. Right, and we're going to consider the case p bigger than q. I mean, you could also study q bigger than p, but it makes more sense for networks to be so-called associative. So things tend to link more with things that are close to them. Okay, and so the idea is now you get a model, you get some random graph, right? Something like this. You can imagine lots and lots of edges, right? A bunch of edges is random. Okay. And now this is the random model, and now the goal is to estimate or recover the communities from the graph alone. Okay, so now I take away, right? I say I color these blue, these red. Now I draw the edges with, more edges, or edges get drawn with more probability if they match to things of the same color, and with less probability if they match to things of different colors. And then I draw this at random, and then, given this graph, I take away the colors, I jumble it all up together, and I ask you, can you find the communities back? Right, for which values? Right, and now the kind of question we want to ask is for which values of P and Q can this be done? Right, so this is now the question, for which values of P and Q can this be done? Right? And keep in mind that we could have, now we can extend this in a variety of ways, right? The most simple perhaps is instead of having two communities, we could have K communities, put n over K nodes on each side, and connect them still if they're in the same one with probability P, if they're in different ones with probability Q. But we can take that further, right? We can make unbalanced communities. We can make the probabilities and their different communities to be different. We can even have overlapping communities. We can correct for degrees, we can give each node sort of an average number of neighbors, so some kind of degree, and then correct the graph to have that kind of expected degree, and so on and so forth, right? There's a whole zoo of variants of the stochastic block model, this being the simplest, right? The two community symmetric block model, right? Symmetric in sort of in two senses, that you get n over 2 split, and that p here is the same as p here. Right? If this p was different than this one, then just the degree of the nodes would look funny, and so it would actually be easy to recover, right? So the most interesting case really is when these two p's are the same. Okay, so now let's try to understand when is it that this can be done. Right, so if, say, p is 1, right, and say q is 0, then I claim the problem is very easy. Right, because I mean, this is sort of trivial again, right? If p is 1, all we're gonna have is just like a completely connected component in one side, a completely connected component in another side, right, and no links in between. Then finding the community is very, very easy. Right, on the other hand, if p is equal to q, then it's impossible. Right? If p is equal to q, then there's absolutely no information in the graph about the communities. Right? The graph is just a very shiny graph. Right? It's just a graph where every edge shows up exactly the same probability, it doesn't matter if they're between communities or not, so then the problem is impossible. Right? So, okay, of course, these are sort of the two complete extremes, but now the interesting question is for which values of p and q are we going to be able to detect the communities, and if so, with which kind of algorithms can we do it? To understand for each values of p and q we can do this, we're actually going to make use of the things we developed with respect to the spike model and random matrices and so on. Okay, so let's start by thinking about what would be an algorithm that would make sense to try. Right, of course, an algorithm that would make sense to try, right, sort of a very natural algorithm is minimum bisection. Right, natural algorithm is minimum bisection. Right. We saw this when we talked about spectral clustering and so on. Right? We just split the graph into two equal-sized pieces as to minimize the number of edges across. Right? So this is a very natural thing to try. Right, and so let's define A, the adjacency matrix of the graph. Right, this has been a player for a while now. Right, so Aij is just 1 if I is connected to J and 0 otherwise. And I'm not going to worry much about what happens in the diagonal. Right, like it won't be important for the algorithms or anything. And sometimes it makes sense to make it 0. Sometimes it makes sense to make it 1. And in the adjacency, the actual thing is to define it 0, but maybe sometimes we're going to loss out loops just to make the math a little bit simpler. Okay, so we take this the adjacency, then we know what the minimum bisection looks like. Right, minimum bisection is just we maximize x transpose AX, right, subject to, well, x is in plus or minus 1. Right, so x corresponds to being plus 1 in one community and minus 1 in the other, and x transpose 1 is equal to 0. Right, the sum of the x's is 0. Right, this means that it's balanced. Right, that takes as many plus 1s as it takes minus 1s, and we didn't see it. Remember, we didn't see it this way. Right, we saw it with minimizing x transpose Laplacian x, but remember, Laplacian is a diagonal matrix minus the adjacency, right? And what this does in the diagonal, it's completely constant because it just sees the diagonals, it just sees xi squared, and those are always 1, so it's exactly the same. Another way of thinking about this is what this is maximizing, right, is the number of edges within, right? Because when we get, this is the sum of Aij, xi, xj. When xi and xj get the same value, you add the edge. When they get a different value, meaning it's across, you subtract the edges. So it's like number of edges within minus number of edges across. Since the total number of edges is constant, it's exactly the same as minimizing across, maximizing within, and all this stuff is all the same. Okay, given that it's balanced, that's important. Okay, so now of course the natural, right? We know this is a hard problem to solve, right? If these things are in general going to be hard, bisection is going to be a hard problem. So what we can do is we can just take the approach of spectral clustering, like we saw 2 weeks ago in the course. Right? I mean, another thing we could do, of course, is to take the semi-definite programming relaxation of Gumans and Williams. Right? The only difference for that is instead of A, we had a Laplacian here because we're maximizing the cut. But maximizing the cut is the same thing as minimizing the cut of the graph complement, right? So all these things are, of course, related. But we're going to start with spectral clustering, right? So let's see what spectral clustering, a variant of it in which we would force things to be balanced would look like. Okay. So let's see if we can get some intuition on what we would get here. Right? So we're going to try to understand what spectral clustering would do, and with the hope that that gives us some understanding of for which values of P and Q we're actually going to expect to be able to recover, in particular with these kinds of algorithms. So the spectral relaxation for this is, of course, just maximize instead x transpose AX such that, right, now we take x to be norm root n, right, the sum of the squares to be n. I mean, this is just a scale, it doesn't matter, but we take away the constraint on each entry and move it to just a constraint on the ultimate one, and x transpose 1 equals 0. All right, so now if you think about this, it's very much like taking the leading eigenvector of A, just with this constraint that it needs to be orthogonal to the whole vector, right? So it's a bit like in spectral clustering how we were taking the second eigenvector. Since it was of the Laplacian and not of A, it was the second smallest one, but right, it corresponds to the second largest one here. But here we're going to do something a little bit different, right? Because we're going to try to understand actually what A is. Since A is a random matrix, we can try to understand what A looks like. In particular, right, if we have a random variable, the natural thing to do is to take its expectation, right? What is the expected value of A? Right? The expected value of A is the matrix where, right, you get an edge with probability P if they're in the same community. So it has a value 1 with probability P and 0 otherwise. Right? So it has the expected value P if I and J, let's say expected value of I and J, if I and J are in the same community. Right? And here I'm considering that, if I is the same as J, they can also get a loop with a probability P, right? That doesn't change anything for the sake of bisection and so on. We'll just make the math a little bit simpler. And Q, if I and J are in different communities, right? But so what is this? Let's assume okay, let's write the community memberships, the true community memberships. This true memberships. Okay, so the true memberships, let's write it as a vector G, right, which is a plus or minus 1 to the n, where Gi is 1 if I is in, say, community S, and minus 1 if I is in community S complement. Right, where, if you think of the picture, I'm making this S and this S complement. Okay, so then, really, so let's continue. For the sake of the analysis of the algorithm, we can label the nodes, like node 1, 2, 3, and so on, in any way we want. So without loss of generality, for the sake of analyzing, we can assume that G is just a vector that is just ones and then just minus 1. Right, so n over 2 of these, and then we're just relabeling the nodes to have node 1 through n over 2 being one community, node n over 2 plus 1 over 2 all the way to n being another community. Right, because without loss of generality, we can do this. Of course, the algorithm can't see it, right, because otherwise, clustering would be very, very easy, right? So the algorithm doesn't know this, of course. But then if I look at the expected value of A, right, what is this? This is just a big matrix with a bunch of P's over here, right? And over 2 of them. A bunch of Q's here, a bunch of Q's here, and a bunch of P's here. Right? Where each of these things is an n over 2 by n over 2 block. But this in particular is a rank 2 matrix. Right? It's not so easy, it's not so hard to check that the expected value of A is actually quite easy to write. It's just P plus Q over 2, 1, 1 transpose, so the whole one's matrix, plus P minus Q over 2 GG transpose. Okay, why? Well, if we're in an entry here, then, right, GI, GJ is just 1, so we get this plus this, so we get P. For here, this is minus 1, so we get this minus this, so we get Q. Okay, so this is completely compatible. So now we can think of A right? We can think of A as sort of signal plus noise, right? Signal here clearly is its expectation, right? In particular, GG transpose is what we want to find. So we can think of A as just P plus Q over 2, 1, 1 transpose, plus P minus Q over 2 GG transpose, plus, right, A minus expected value of A. Right? In a way, we can think of this as the noise, right? And this is the signal, right? In a way. Now, we're very much getting into the spike model type thing. But remember that what we wanted to compute wasn't exactly the maximum eigenvector, right? It was something more like this. So in particular, right, in particular what this means is that what we want is orthogonal to the whole one's vector, right? So if we subtract or add any term that is like 1, 1 transpose, right, since X is orthogonal to 1, 1 transpose, when I take X transpose, right, if I were to add or subtract anything that's a multiple of this, X transpose 1, 1 transpose X is 0, so we're never going to see it. So what we're going to do is we're going to replace A with something that we're going to take away this term. Because this term is known, right? There's nothing to learn on it. I know it. Of course, maybe I don't know exactly what P and Q is, or maybe I do. That's not actually a problem. You can very easily estimate P plus Q. And what I'm going to do, I mean, you could also just subtract a different term. It's fine if it's not exactly this, but for the sake of the analysis, we're going to subtract exactly P plus Q over 2. But if you subtracted something bigger, everything would still work, nothing, there would be no problem. But okay, so let's say that we take then this sort of adjusted matrix, calligraphic A, which is going to be A minus P plus Q over 2, 1, 1 transpose. Okay, and we're going to now do things in this matrix. Okay, why is this better? So the point is that now it will look like a spike model where there is a rank 1 perturbation to some noise that is mean 0. Right? Maybe the distribution of this noise is complicated. We'll deal with it. But another important thing is that now we can actually drop this constraint. Right? This constraint was here precisely in a way to avoid just trying to match this term that's sort of not meaningful, right? Not informative. But now that we subtracted this, if X were to correlate a bit with the whole one's vector, then we'd get a big negative penalty from here, right? Because whatever this value is, right? Let's say this value is 2, right? We'd get basically 2 squared from here. So we get P plus Q over 2 times 2 squared negative term, right? And so this is a bit like a Lagrange multiplier, right? We move the constraint to a penalty in the objective. And even if this is negative, because we would see the square, right? Because we would see X transpose 1, 1 transpose X, it would still be positive here, and therefore it would still be a negative contribution. Right? So instead, what we do is we take the following problem. And we take max X, now just L2 norm N, but you know, it's just a scaling, so it's fine if it was N or 1 or anything like this. Just H transpose calligraphic A X. Right, and now the question is, when does the solution to this is good or estimates the communities. Right? Another way to say this is, when does the solution to this correlate with the true labels G? Right? When does it correlate with G? But if you think about it, this is just the leading eigenvector of A. Right? So really the question is, when does Vmax of this matrix A correlate with G? Now, if calligraphic A was a Wigner matrix plus a Rank-1 perturbation, we would know how to answer this question. Right? In this case, we don't. Right? So if A was Rank-1 plus Wigner, right, we would know how to answer. Right, but it's not, right? A is Rank-1 plus a random matrix that's not Wigner, right? The centers are not Gaussian. They are some Bernoulli, right? Some centered Bernoulli random variables. Right, but so we can still try to understand at least, right? Still a reasonable goal to try to understand when is it that the maximum eigenvector, the leading eigenvector correlates with the true communities G, which corresponds to the Rank-1 spike. So we can rewrite, right? We rewrote this with calligraphic A, which is given by a Rank-1 spike plus noise, but it is not, right? A Wigner matrix plus a Rank-1 spike, right? The noise has a different distribution. But let's say for a second that it was. Okay, so let's rewrite this. Okay, let me just rewrite it. It's easier. So A will be equal to P minus Q over 2. B G transpose plus A minus expected value. Okay, so we're going to think of this again as the signal, and this is the noise. Okay, now what we're going to do is we're going to make a prediction. Right, this one will be non-rigorous. And in fact, I mean, the prediction will turn out to be accurate, but it cannot be, you know, the theorem can't be proven this way. Okay, so if we have that A was equal to some lambda VD transpose plus W, where W was Wigner, say with entries and 0 sigma square, then we would know how large lambda needed to be in order for the leading eigenvector of calligraphic A to correlate with V, right? Which is exactly what we want. We want to know when is it that the leading eigenvector of this matrix correlates with G. Okay, so if this was the case, then we know that the spectrum, right, the spectrum of W lies in a semicircular law somewhere between minus sigma root n to 2 sigma root n. And so we would expect, I mean, if these were really Gaussian and so on, we would know, not just expect, that V max calligraphic A correlates with V if basically if we had that lambda was bigger than right, so it's 2 sigma root n over 2, right? Because we know that we did this on the class before. What we need is for basically the spectral norm of the Rank-1 spike to be half of what the spectral norm of this is, and then you start seeing it, right? Because of this because of this push-out phenomena that, this pull-out phenomena that we talked about. Okay, so let's just pretend that this was the case. Right, so if we had something like this, then for here, what would this predict? Right, this would predict that we would need, okay, so let's rewrite that. Right, so P minus Q over 2 GG transpose. Right, we need to write it to have the norm of BB1. So we would need P minus Q over 2 G over root n, right? Because G is plus or minus 1, so it has more than root n. Right, so we divided by root n, we need to add an n here. Right, because we divided by root n twice. So we would need that n P minus Q over 2 is bigger than 2 sigma, or I can take away the 2, sigma root n. Right, but now the entries of the noise are not Gaussian, right? Entries of calligraphic A minus expected value of A are not Gaussian. Are not normal, 0 sigma squared. In fact, they're not even identically distributed, right? Entries in the same that correspond to things in the same cluster look different than entries that correspond to things in a different cluster. Right? So what is the variance of these entries? Right, what is the variance of entries of entries of A, right? Or of A, I mean, the variance of an entry or an entry minus the expectation is the same. Right, basically what we have is they're Bernoullis, right? They're Bernoullis, they are Bernoullis P if in the same cluster, or Bernoullis Q if in different clusters, right? So basically the variance is, right, the variance of a Bernoulli P is just, right, it's P times 1 minus P. Right, so we have that the variance is P times 1 minus P if for entries corresponding to the same community. So if I and J are in the same community, and Q 1 minus Q otherwise. Right, so if you think of the matrix like this, the variance is here is this P 1 minus P. Right, these are the variances. Okay, so a reasonable thing to do is to say, I mean, of course, you know, this will have to be justified quite carefully, but a reasonable thing to do, again, non-rigorous, we should make that very clear. Right, we're going to take the variance in this prediction to be just the mean of the two variances. There's going to be P 1 minus P plus Q 1 minus Q over 2. Right, this is like a guess. I mean, this is just a heuristic. Okay, since I don't have the same variance, I'm just going to take the average of the variances of the entries. Okay? Seems reasonable. Right? And now I get this, and now let's see what my prediction would be. So prediction, okay, prediction. It's possible, and in fact, with something like spectral clustering, to learn to estimate communities, the communities, or memberships, if the following holds, right? Let's see what the inequality gives. N P plus P minus Q over 2 is bigger than, and now we get square root of that big thing. So let me take the 2 over here. And now we get square root of P 1 minus P plus Q 1 minus Q times square root n. Okay, we can make this a little bit nicer. Right, but it's already kind of cool that we're getting, right? The bigger P is with respect to Q, the easier it becomes. Right, so it's starting to look reasonable at least. Right, so we get square root n, and then the square root 2 cancels over there, square root 2. Right, the root n went over there. P minus Q is bigger than square root. Okay, so let's let's now test this prediction, or let's now see what this would give in some cases. So it turns out, in the cases where this heuristic is the most okay, right, is when these numbers are actually the same, right? The case, let's look at the case when variances are the same. Right, so P times 1 minus P is equal to Q times 1 minus Q, right? So if we want them to be different, otherwise not interesting, we get 0 here. We can just make P be, or let's make Q be equal to 1 minus P. Right, so we expect both of them to be something like, P to be something like 1/2 plus epsilon over, or let me say, 1 plus epsilon over 2, and Q to be 1 minus epsilon over 2. Right, so that their difference looks just like epsilon. We're going to take epsilon small. And let's see how small we can get epsilon to be. And in this particular case, the argument can actually be established. Right, in this particular case, the argument can be made precise. Okay, so what would we get? In that case, we would get root n over root 2. Epsilon, right, P minus 2 is epsilon, is bigger than, and then essentially something like, right, 1/2 times 1/2, right, I mean, the epsilons won't matter so much, plus 1/2 times 1/2, right, so something like actually, so 1/4, plus 1/4 is 1/2, 1 over root 2. So we get something like epsilon needs to be bigger than 1 over square root n. Right, this is quite incredible, right? It's saying that we can already start to get some information about the communities already when P is like 1/2, right? When P looks something like 1/2 plus something like 1 over 2 square root n, and Q is equal like 1/2 minus 1 over 2 square root n, right? The difference is quite small, right? It's in the order of 1 over root n, we can already see it. Okay? And for this particular case, the argument can actually be salvaged. But an even more interesting regime is for sparse networks. So sparse networks make a lot of sense when modeling many things, including, for example, social networks, right? What one means usually by sparse networks is we don't want the average degree of a node or the neighborhood of a node to look very different as we make the graph bigger and bigger, right? If your probability of connection is like 1/2, if there's like, right, 7 billion people on Earth, then if you think of a social network, the probability of connecting is 1/2, you would be connected to like 3.5 billion, right? But we don't expect the size of our social network to really depend on the size of the world. So it makes sense that the average degree of the connectivity should be constant or almost constant as the network grows. So a very natural thing is to take P to be a constant times A over N, and Q to be another constant times B over N. Right, the nice thing with this is that the expected value of the degree of a node, right, does not depend, is constant. Right, it's something like A plus B over 2. Right, it's constant with the size of the network. In particular, the average, right, the expected value of what we call in degree. So the number of connections within your community will be something like A over 2, right? Because you have something like N over 2 possible connections. You get probability A over N of each one, so you get A over N times N over 2, you get A over 2. And out degree, you get something like B over 2. Right, but the point is that this is a very, very interesting regime exactly because you do not, right, your sort of neighborhood and your degree, your number of connected nodes does not depend on the size of the network. Right? So it's a particularly interesting one to study. Now we can see what we get then. So let's see, let's just replace. Right, so for sparse networks, okay, for sparse networks, what we get, root n over root 2. Right, now we get A minus B over n bigger than, we get A over n. Now we get 1 minus A over n, but this is just 1, right, because n is so much bigger than A. So we can keep track of it for now. It's B over n, right, but this is essentially, I mean, as n goes to infinity, this is basically the same. as right, as having, okay, let's say, so, and a root n survives, so we get a minus b over root 2 root n bigger than square root of a plus b over square root n, right? The n from here and a plus b, we just ignore these terms, these are basically going to 0. Same thing here. Right, and now we take squares of everything, the root n's cancel, we take squares of everything, we get this super nice expression. Okay, think about this, this is kind of incredible, right? So what we're saying is that in a sparse network, recovery is possible, maybe with the spectral algorithms, if a minus b squared is bigger than 2 times a plus b. So although this heuristic, the heuristic that I described cannot, doesn't work, like the algorithm, when things are not very sparse, it still works, but when things are sparse, the spectrum of the random matrix is very different. It produces a prediction. Turns out that now we know that this prediction is completely accurate. So now we know it's a theorem that if this is satisfied, then it is possible to estimate, at least better than a random guess, the memberships of the communities. However, it is not the case. It is completely impossible to estimate the communities better than random. Now, there's a lot of cool stuff going around this. One is that the way this was predicted at first was using statistical physics, ideas from statistical physics, maybe from now, like 10 years ago or so. So the idea is actually quite cool. There's a few ways of making these predictions, one of which is to think of the dynamics of something like belief propagation. So if you think of each one of these nodes, trying to compute the probability that they are in one of the communities versus the other, right? You can think of this as some kind of Bayesian model where the communities get drawn first at random, and then you draw the graph, and now you want to know the values of the communities conditioned on the graph. And so now we can think each node is trying to compute this posterior distribution. Now as they're computing, they do it via belief propagation, which I will not describe in detail, but essentially amounts to looking at the beliefs of all your neighbors and pretending that the joint distribution of the neighbors is actually just the product distribution of the marginals of their beliefs. Right? If one thinks their probability 2/3 of being +1 and 1/3 of the other one 1/3 of being +1 and so on and so forth, you just think, okay, let's say that the joint distribution is just the product of these marginals, and now you use Bayes' rule to compute your marginal. Right, and now then you give your marginal to everyone else, and you run this process a few times. Right, you need to be a bit careful to not send back the same information and so on, but I don't want to get into details. And now you can try to study the dynamics of this process, at least on average. In particular, this process has a fixed point, right? Well, it should have a fixed point, hopefully, in the true solution, the one that we want to find, or at least something meaningful. But there's sort of a very bad fixed point, a very non-informative fixed point, which is when everyone believes they're half +1, half -1. Then I look at all my neighbors, everything is symmetric, I have no way of breaking the symmetry. So this is a very uninformative fixed point. One thing you could ask, come from physics, studying dynamical systems and so on, you could ask, is this fixed point stable? Is it stable to small perturbations? And if it's stable, this is probably a bad sign, because you're going to start with very little information, so you're going to start pretty close to this. So if this is stable, you're probably going to fall there and get completely uninformative solutions. If it's not stable, maybe you'll go somewhere else that is informative. And this is one of the possible natures of predicting this. It's exactly the place at which the fixed points, the uninformative fixed point stops being stable. So it turns out that this intuition is completely accurate. We now know this is the truth. We even know that if you're below this, the graph just looks essentially the same as if the probability was the same in edge and across edge, if it was just a plus b over 2 on both. Especially these graphs are so-called contiguous. There's no real way of distinguishing them. I don't want to get much into what contiguity is, but the idea being that there's no statistical test with full power that is able to distinguish these models. When this is the case, then we have algorithms that can actually work. We still don't quite know if the vanilla belief propagation works, but some adaptations of it do work. Then another really fascinating phenomena here, well, okay, there's a big fascinating phenomena that, using the ideas from statistical physics, we're predicting very interesting things in sort of learning, data science, and random graphs. The other really interesting phenomena is that if you take more communities, if we take this with K communities, right, we can still ask the problem for K communities. Right, the exact same problem, where maybe we do, say, 5 communities. So maybe we have this. Right? Each one of them we can over 5. And the same thing, we connected probability Q and we connect probability Q and probability P if they're in the same community. And now we can ask the same question. And we can still study the same, right? There'll be some form of, you can think of some form of signal to noise ratio. Right, the signal to noise ratio here was something like, right, was something like A minus B. In the other model, this was, you can think of this as the signal to noise ratio, right? If this is bigger than 1, you can do it, otherwise you can't. The bigger this is, the easier it is. Now, it turns out that this really, really fascinating phenomena happens for 5 communities or more, which is that there is a place, right? So this is called, this is known as the Kasten-Stigen threshold, is the one that corresponds to something like this. Right, but for K communities, I mean, there's no point exactly what it is, there's no point in writing exactly what it is. But there's a point above which sort of, this is the point where the fixed point becomes stable. And we believe that here the problem is easy, in the sense that it can be done with, you know, efficient algorithms and so on. But we believe that there's another region here where the problem is possible but hard. And here the problem is just impossible. So this does not happen for 2 communities, but we believe, or we conjecture, that it happens for 5 and more, and maybe for the. So this is a very strange phenomenon, which is that when we're past a certain threshold, we can do it with maybe belief propagation like methods, spectral methods, as we'll talk also about STPs and so on. Below this, it seems inherently difficult that we don't know any efficient algorithm to do it. And then, but then the place where statistically there really stops being information in the graph about the problem enough to recover seems to happen much later. Right, and so this is a super interesting region, because this is a region where sort of information theoretically, statistically, solving our problem is possible. However, if we're bound by restrictions on computation, which we are in practice always, especially now as data sets gets bigger and bigger, this will actually, you know, even if not impossible, if it takes exponential time, it's completely impossible in practice. And so if you want to study the limits of learning, you know, as data sets grow bigger and so on, we really should be studying these thresholds and not really these ones. And so one thing that I'll try to hint at a couple times in this course is talking a little bit about the difference between these two, and this is a very nice example of this. Now, let me just make the comment that, you know, NP hardness traditionally doesn't say much about this type of phenomena, because if the problem here is to minimize, I mean, maybe not the minimum bisection, but the minimum, say, 5-way cut, right, cut into 5 pieces. This problem is, you know, doesn't change as the graph changes, right? The problem from the viewpoint of worst case computational hardness is always the same. So in a sense of sort of NP hardness, just an NP hard in one, you know, it doesn't, the definition of NP hardness doesn't have the distribution of the graph inherently to it. So the traditional hardness of the problem is still the same, right? But somehow as the graph, right, this idea that as we have more and more data, better and better data, not only things get better statistically, but they also get better computationally. You also need less computation to do it. And so in what follows, what we're going to talk about is we're going to talk more about not just partial recovery, but exact recovery, recovering every membership correctly, and about semi-definite programs, where we're actually going to prove that we can succeed in certain regimes. Well, here all we give was an heuristic to sort of get a feel for what are the right parameters. All right, thank you.